So, next graph, the third and the final one is dependence graph. It comes in the context of certain architectures called array architectures. Prominent array architecture is systolic array. Dependence graph, like the SFG and also the DFG, it also consists of two things only. One is nodes indicated by bubble, meaning task, computation, etc. and directed edges same as before. But there are two differences. One is no operation including delay, constant multiplication, etc. are allowed along the edge. Remember, in the case of SFG, we allowed certain operations like delay and also constant multiplication in the edge. In the case of DFG, constant multiplication was ruled out, but delay was allowed. Here, none of them is allowed. That is one thing. On the other hand, in both SFG and DFG, I had nodes, one node dedicated for one job, and that it was doing again in all cycles, NS cycle, n plus 1th, n plus 2th, same node. But here, each node will not be reused. And instead, they will be copied, they will have multiple copies. Let me explain. Actually, dependence graph is the trickiest of the three. It requires proper understanding. In the case of say SFG or DFG, consider a particular node. So, node was taking some data in the NS cycle, current cycle, producing something. Then again in the next cycle, it is again taking another data, again producing another thing by the same operations and so on and so forth. So, iteration after iteration after iteration or clock after clock after clock, the same drawing, same node was working again. Here it is not. Here I will have several copies of the node drawn in my diagram. One copy will work in a particular nth cycle, another copy may work in the n plus 1th cycle, another copy may work in the n plus 2th cycle like that. Okay. So, no reusing. Now, unlike the SFG and DFG, as I told you, dependence graph is the trickiest because it requires certain intuition to draw it. I mean, there is no systematic procedure of teaching you how to draw dependence graph. You have to look at the problem and then you have to use some imagination. It comes just by practice. We will take some example now. Okay. Now, when you draw dependence graph, what is the advantage of dependence graph? You will see that a very regular pattern of connection and nodes will emerge. I mean, whatever with the appearance in a particular sector, the same thing will repeat here. So, this is very good for VLSI realization, because in VLSI what they do, they produce a mask of a particular spot. And then you keep repeating the mask again, the entire circuit builds up. Okay, that is why it is very good for VLSI relation. Also all connections are local, you do not have to take a wire and route it through the network, all local connections, okay, very little propagation delay, and you can pipeline all the edges, putting delays, all these things make this dependence graph very useful, because it leads to the final architecture called systolic array or array architecture. Okay. Now, in the heart of the dependence graph is a basic processing cell or processing unit, which you define separately, that okay, this is the basic unit I will be using, that will be by node, it will take this kind of inputs and it will generate these outputs by such and such computation. Once you define that in a diagram, then use it in the main diagram again in multiple places, the same copy, it is copied here, everywhere, and depending on the problem at hand, the various edges will form connecting one node to another node, and that entire DG will come up. All right. Let us take an example. Consider again the good old FIR filter. Theoretically, it should be from n equal to minus infinity to infinity, and this summation also, and ideally should have not only just 3 terms, x n, n plus 1, n plus 2, like that. It does not matter if it is non causal or causal, n minus 1, n minus 2, n minus, but here we are taking only 3 terms, and also we, for our convenience, we assume that it is switched on meaning and of course, if there is no input, there is no output. So, this is also 0 for this. Okay. Then we will consider the implication of that actual equation if where x n is, we are starting from n equal to minus infinity and going on, and also we have got infinite such terms, not only just 3 terms, x n minus 1, x n minus 2. Okay. But that is later. Now, let us look at this problem. What is the basic operation we are doing? Consider this. There is a built-in constant, that times an incoming data output. So, multiplication, then adding with something. So, this we do first, adding with 0. So, multiplication into, B0 into this, a multiplication plus 0, this is the result. Next time, again same job, a multiplication with the built-in constant, multiplication of a data, and then add with a data. Earlier it was 0, now it is data, and then whatever is generated, now you come here again a built-in constant time a data plus whatever is generated. So, multiplication and then multiplication output with plus with something already generated. Okay. So, multiplier and accumulator, multiplication and accumulation, MAC. So, we define a processor first here, a processor node. How to define it, how to orient the various lines. See, orientation of the line, like this is vertically up, horizontal, all this come out of practice. The orientations you choose matter a lot, but they come out of practice. There is no systematic way of explaining how to do, it just comes out of practice. So, I define a node, basic processing node that has 3 input incoming edges, one is this, one is this, one is this, and 3 outgoing edges, one is this, one is this, one is this. So, it works on the incoming data, this, does something and generates one output here, one output here, one output here. How to explain, how to define? We just give a name to these variables, say let us call it B and let it be B prime. Let us call it x and let it be x prime. Let us call it s prime. Then we give a definition, whatever b comes in, the same b is pushed up, is moved to the right. So, b prime is same as b, that is b just passes through. Oh. Very sorry for this. This is the problem of high tech. Even if I do not touch the board, if I go close to the board, it just gets erased. Similarly, whatever x comes in, that passes through, and you got x prime. So, x prime is x, and in the case of s prime is the actual s for summation. So, incoming thing plus b into x, like b into x plus incoming thing, this is like s and b into something. So, b into x. So, s prime is the result of this together is s plus b into x. This is how we define our basic processor. Then I define, then I draw the array like this. This is by 0 0 location, the coordinate axis. This is, though I am writing some line here and line here, I am actually actual axis will be here and here. This is by 0 0 location, I put a bubble here. So, this is one node located at 0 0. So, here, for 1 minute. I have a node here. In 0 0 location, then I put a node in 1 0 location, one in this direction, and then we give a j. So, 0 0, there is n 0 j 0, this is at origin. Okay, this is not the origin, this is a reference from a drawing, this is the actual origin. Then 1 comma 0, 1 means n goes up to this n direction, n goes up by 1, this remains 0, 1 0 location. Then I draw here 2 0 location, 3 0 location, goes on. I would have had on this side also, but that I am coming later, that I will consider later. For the time being, we will have here. Why here? That when the array is formed, you will see easily what is the function of this. Then dot dot dot. Similarly, another integer coordinate, these are all integer coordinate points, 0 comma 0, 1 comma 0, 2 comma 0, 3 comma 0. So, both the n value and j value are taking integers 0, 1, 2, 3 like that. Similarly, this is 0 comma 1, n is 0, j is 1, this is 1 comma 1, n is 1, j is 1, 2 comma 1, 3 comma 1, 4 comma 1 dot dot dot, and then again I have got 0 comma 2, 1 comma 2, 2 comma 2, like this, all right. Then I give input say x n. Now, whatever x n goes in, that will, by this definition, that will go up, and there is an incoming edge from bottom to this node, and they will join. Okay. That is, from this node, this is an outgoing edge, and from the bottom node above, there is an edge from the bottom, those two get joined as one common edge forms. Similarly, this gives rise to one edge outgoing, and there will be an incoming, and they get added. Like that. Similarly, here I give x n minus, sorry, I give x 0 here I give x 1. I give x 2, because as I told you switched on at n equal to 0. So, all data before x 0 are 0. That is why the left side is not there. There is no x minus 1, x minus 2, x minus 3. It is only x 0, x 1, x 2. That is why I am getting on this right hand side. And j, we will very soon see what is the meaning of j. Let me complete this. I hope you are understanding that this is a bottom edge, these are edge above. This is the edge above. And again, this is the bottom edge, and they add, they are not aligned. These two edges add, the join. This is x 4 and dot 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 dot. On the B side, there is an edge, this I give the coefficient B 0. As you know, whatever B comes in, that passes through, the same thing comes out, same B 0 will come out, there is outgoing edge of this node, and there is an incoming edge of this node incoming here, outgoing here, and they join. So, forms one common edge, same phenomena here, and it goes on. That means, same B 0 moves in the same cycle, same B 0 moves through all of them, I mean it goes to all of them. Then here I have the same thing, but now B 1. Okay. This is B 2. So, understand j is nothing but this index of B, B 0, 1, 2. So, j 0 here, j 1, j 2, 0, 1, 2. I do not have j minus 1, because that means that I would have had x n plus 1, n plus 2, but those terms are not here because I consider a causal FIR filter. But theoretically, it should go to from B 0 to B minus 1, B minus 2, B minus up to B minus infinity, and B 1, B 2, B 3 up to B infinity, and the same thing, and x n also should have been there from n equal to minus infinity onwards to plus infinity. There is n should go from minus infinity to infinity, j should go from minus infinity to infinity. The entire plane I would have had these nodes at all the integer coordinate points. Remember, all are integer coordinate points. But in practice, we are not doing it. We are making it causal. That is why left hand side is not coming. Also, we are switching on at n equal to 0. That is why the bottom half is not coming. Only the first quadrant coming. But ideal array, ideal DG would have assumed the same kind of pattern all throughout, from n minus infinity to infinity, j minus infinity to infinity. Okay, and all integer coordinate points to be filled in just by one node and do nothing. The various incoming outgoing edges join and the array is formed. I have not yet done the S. So, let us start with the S. I will fix the value 0 here, I will tell you why. So, this is outgoing, the incoming and they join. Again outgoing, incoming, they join. so on and so forth. Let us start at any this node. What is this doing? X of 0 going in, B0 going in, B0 into X0 plus incoming 0, that will come here. So, what is coming here is B0 X0. Now, what is Y0? Y0 means B0 X0 and then B1 X minus 1. X minus 1 is 0 because it is switched on at n equal to 0, X minus 2 is 0. So, that means Y0 is nothing but B0 Y X0, B0 X0. That is why I have given 0 here. So, previous computation from this side is yielding 0, with that B0 X0 only, B0 X0 coming getting. So, what I am getting here is Y0. Now, the same X0 moves up, B1 here. So, B1 into X0 plus 0, that comes here, B1 into X0, B1 into X0. Now, B0 moves out and X1. So, B0 X1 plus B1 X0. This was Y0. What is Y1? Y1 will be B0 X1, B0 X1 and B1 X0, B1 X0. Nothing from here because it will be B2 X minus 1, which is 0. So, this is equal to Y1. So, Y1 is coming here. Same X0 moves further up here. I have got B2 X0 plus 0. So, B2 X0 that comes here, same B1 is moving, B1 and now same X1 moving. So, B1 X1 plus that. So, B1 X1 plus that, result is here. Now, X2 and same B0 moving. So, B0 X2, this will be Y2, you can easily see, if it is Y2, B0 X2, then B1 X1, then B2 X0, so it will be Y2. In the same way you can verify, it will be Y3, Y4 like that. Okay. So, this is a DG, dependence graph, you see all connections are local, whatever is the pattern in one place, there is this pattern, you design a mask for it. And when you design the IC, just put the mask here, put the mask here, put the mask here, put the mask here, mask here, and all the incoming outgoing edges join together and this very regular structure comes. There is nothing haphazard in this structure, nothing irregular. That is why it is very, very useful, very good for VLSI design. And all the interior coordinate points 0, 0, 0, 1, 0, 2, 0, 0, 1, 1, 1, all the interior coordinate points you fill in the put that processor. All the edges they get added, they get joined, they join hand in hand, depending on their orientation, this comes up. Now, while doing that, ideally I should have had that entire plane from n minus infinity infinity and j minus infinity infinity should have put this, nodes, but here there is a departure. This should have come from another processor here, but instead of that, I am forcing the value to be 0. This should have come from another processor here, instead of that, I am forcing the value 0 because there is nothing beyond X0. If there is a processor here, that would have taken X minus 1, but X minus 1 is 0. So, that is why I am forcing it to be 0, forcing it to be 0 like that, because initial value is 0. Initial value is 0. Similarly, I am not going below this, but ideally I could have had B minus 1 x n plus 1 plus B minus 2 x n plus 2 like that. Okay. So, I should have had more lines. X0, x minus 1, x minus 2, x minus 3 up to x minus infinity, x1, x2, x3, x4 up to x plus infinity, and B0, B1, B2 up to B infinity, and B minus 1, B minus 2, B minus 3 up to B minus infinity. That is the entire diagram. Entire plane, just hit all the coordinate points, integer coordinate points, put this processor there happily, and the edges will join hand in hand, and the entire actual DG will come up. It is a truncated DG. There is a DG on which we have done some kind of further restrictions. We have enforced some manipulations like 0 fade here, and then I am not allowing it to go below, I am not allowing to go to the left, and so on and so forth. It is a 2-dimensional DG. As I told you, drawing a DG It's not an easy job, it comes out of practice. Okay. What is the meaning of DG actually? I mean, I can come back to this page. Suppose I have to write a program, computer program to evaluate yn, okay, equal to b0 xn plus b1 xn minus n, write a program. Okay. What should be the program? That is why I have got, for your sake, I am rewriting that equation. Your program will be computer program, all of you know, for n should have been from minus infinity, but as I told you, we are enforcing the fact that system is switched on only at n equal to 0, and before that everything was 0. That is why we are not going for ideal DG, we are going for a truncated DG that starts at n equal to 0 and can go up to infinity. For n equal to 0 to infinity, have a value s equal to 0, then have an inner loop. This is a computer program, I think this does not require any explanation. For j equal to here 0 to 2, new s will be old s, this is the MAC operation, old s plus bj x n minus j, and then yn will be this s end. We can easily see, we can easily verify this. Start at n equal to 0 and s is 0. So, if n is 0, what is happening? At j equal to 0, 0 minus 0. So, b 0, or maybe for any general n, phi n equal to 0, take any general n, s is 0. So, now get into this slope, start with 0 here, s is 0. So, new s will be b j equal to 0 now, b 0 x n. So, b 0 x n. Next time j equal to 1, so it will be b 0 x n, j is 1, so b 1 x n minus 1. So, b 0 x n plus b 1 x n minus 1, together will be new s. Next time that plus b 2 x n minus 2, that will be final s, that I take to be y n. This is the program. Now, how many loops are there? Are 2 loops, one is inner loop, another is outer loop. Okay. There is one loop index n, another loop index j, and this is the basic processing. You will see my DG was two dimensional DG. One axis was n, another j. N was taking various integer values, j was taking various integer values, and for a particular n comma j pair, there was a processor of this kind: incoming s plus multiplication and accumulation, incoming s, incoming b, incoming x, they are multiplying, adding with incoming s, new result. So, that means typically we may have something like this. For suppose I take an example, for I equal to maybe some value to some value, some start to star, then again for j equal to another start to star. Star means some value to some value, I am not bothered about that. Maybe I have got another one, k equal to some value to some value, but integer values, and maybe for L equal to, you have the basic operation where you evaluate, like here evaluating s, you are evaluating some function, which is a function of I, j, k, L, that we evaluate by a formula, by some calculation like this, and then end. And an example. So, here you will have a 4-dimensional DG, one axis will be I, another will be j, another will be k, another will be L, and they all take integer values. As you know, in computer program you write for I equal to maybe 1 to 10, you do not have I equal to 1.5, 2.5, 3.6, not like that, they take all these loop indices take integer values. So, I take integer values, j take integer values, k takes integer values, L takes integer values, and for each quadruplet I one value, j one value, k one value, L one value, you evaluate this. So, you have a 4-dimensional DG, one axis I, one axis j, one axis k, one axis L. You design a basic processing cell that generates this. So, depending on the integer values of I, j, k, l, you identify that integer coordinate point, put that processor and do it for all the i's, all the j's, all the k's, and that entire 4-dimensional DG will come up. Unfortunately, we cannot draw it because it is 4-dimensional, but it will be a 4-dimensional DG. This tells you about the dimension of the DG. Dimension is nothing but number of loop indices to run the program. Each loop index is one axis. Okay, number of loop indices to run the program. Here I had got 2. Okay, that is why there was one axis n, another is j, 2-dimensional. But it does not have to be 2-dimensional. You can have any dimensional, 10-dimensional, 15-dimensional. Then the question is, when it goes, if it is a 1-dimensional DG, I can directly implement it on IC. It will be one string, one line only. That is called a string. If it is 2-dimensional, it will be plane. That will be called a planar IC. Planar. That is a plane of an array on a plane. If it is a 3-dimensional, it will be called a cube. Okay, cubic. So at every integer coordinate points in the cube, we will have some processors. Okay, cube. But if the dimension goes beyond 3, like 4, 5, 6, 7, 8, 9, 10, you cannot realize in IC because the whole world, real world is 3-dimensional. So you cannot realize a 4-dimensional DG on an IC or a 5-dimensional DG on an IC. Then what we do is we map a higher dimensional DG to a lower dimensional DG. Lower dimension can be 3 or 2 or 1. Okay, that mapping is called systolic transformation, which we will consider, I mean, if time permits, we could consider later. Okay, that systolic transformation by which we map a high dimensional DG to a lower dimensional DG. Okay, and so that the lower dimensional DG, as you know, is realizable because its dimension is 3, 2 or 1, realizable. Okay, that is the entire philosophy of array architecture design. So, this much we have for the this thing, for this graphical representation of DSP algorithms. Okay, graphical SMG we started with, then we covered DFG, we covered a very important topic called critical path there, and also told you about retiming, and then separately we have come to another interesting architecture which is very useful, another interesting signal graph which is very useful for a particular kind of architecture called array architecture, that is dependence graph. So, that covers the first topic, and then as I mentioned about retiming, this is what I will be spending considerable time on, and there is something called retiming theorem, which I could skip, but I feel that I should prove that theorem in the class. You have to bear with me, because then only you get an idea about, I mean, why you follow this particular retiming formula, where it comes from. Otherwise, it might look little boring as to where from a particular retiming formula is coming. So, I will spend some time on retiming theorem proving, and of course, then from retiming theorem various things follow, and slowly we go to a practical way of doing retiming using, of course, retiming theorem. Okay, we cannot violate retiming theorem, and that practical way is called cut set retiming. Okay, and then we take some examples and show you how to do retiming to achieve some particular critical path target. Okay, so that takes me to the next topic. Retiming means you are given a data flow graph, and there are various edges, some edges having certain delays, some edges are not having delay free. You can calculate a critical path also. Now, retiming tells you a way by which you can alter the delay values in various edges without violating the functionality of the original graph. That is, it will be new one will be equivalent to the old one in terms of the output that it generates for a particular input. As I told you, equivalence may be little loose here, it is still equivalence, very much equivalent, but it may not be very rigid equivalent. That is a particular node before retiming and after retiming may produce the same output, but the two outputs can be delayed version of one another with a known delay. So, by appropriate shifting forward or backward from one you can get back the other, because the delay is known. So, it is equivalence in that sense. Okay. Of course, it is equivalent because I am not losing any information. If I know the current output, if I know it is delayed by say delayed from the original one by say 5 cycle. So, I will move it up by 5 cycle, I can get back the original one because 5 is known to me. Okay. Similarly, something scaled up, like a node is generating a sequence say xn. After retiming, if it generates 10 times xn, if I know the factor 10, so from the current output, if I divide by 10, I can get the original one. So, it is equivalent, of course, very much equivalent, but there is little flexibility there, okay, because if you do not allow the flexibility, then things become very tight and you cannot do many many optimization techniques like retiming and all. So, with that, consider a DFG. Any part of DFG will be typically of this form. There will be one node, another node, there will be an edge. Edge may have a delay, may not have a delay. So, I write W, actually W times D. W can be 0, means 0 delay, 1D means 1 delay, 2D means 2 delay, like that. Let me call it U, let me call it V. Okay. You may write some amount of time T here, T. So, T microsecond may be spent here, T microsecond, it is T, it can be T prime also, why only T. Okay. This is given, W amount of delay. This is a typical sector of a DFG. A DFG is nothing but repetition of these things. One node, an edge comes out of it, hits another node with or without delay. Again, from here another edge comes out, hits another node with or without delay, and goes on everywhere, and the entire DFG comes up. So, I do sector wise, I take the basic sector. Retiming theorem says that choose integers. It can be positive, 0 or negative, but this is purely your choice. You are absolutely free. You can choose certain integers, okay, 1 for each node, 1 for each node. Okay. So, assign, you choose one integer, assign it to one node. You choose another integer, assign it to another node. Choice is yours, positive, negative, 0, no problem. Okay. Then this will be called retiming value of the node. Like if I choose value 2 and give it to U, then node U will have retiming value 2 and so on and so forth. So, you denote by R for retiming, R bracket U as the retiming value, that is an integer for node U. Similarly, R of V, retiming value for node V. These are the integers you have chosen. Then retiming theorem says that this will be equivalent to same U, same V, same connection, but delay will be W R times, R for retiming, new value, where W R will be original W plus retiming value of the destination node where the arrow is hitting, that is R of V minus R of U, source node. Source in this sense, in a limited context, in this, for the edge, this is the source, this is the destination. So, retiming value of destination minus retiming value of original source with that original delay, that will be WR. Only constraint is, since there is a negative sign, you should choose this value such that this does not turn out to be negative. That is, you must choose RV, RU such that for every pair the WR, when you wrote that, it should be greater than or equal to 0, because negative number of delay has no meaning. Okay. It might appear to be something easy to you, that okay, why not increase RV, take less value of this so that it is always positive. But if you have a loop, suppose this has W1, this has W2. So, now this will become W1 will become equal UV, W1 will become W1 plus, because the arrow is here, R of V minus R of U. But in the case of W2, arrow is hitting this side. So, this is the destination, this is the source. So, it will be reverse of this, W2 plus R of U, because this is the destination now, minus R of V. So, if you want to make R of V very high, R of U less, so that you are happily, you are happily in a situation where this is positive. Okay, you are very happy, complacent that this is very positive, because you have taken R of V to be high, this to be low, very good. So, this is positive. But then there will be a reverse effect here. R V very high means this will be highly negative, R U very less means very less positive. So, this, by trying to make this positive, you may end up by making this negative, which is also not allowed. So, it is not an easy thing for every pair. When you apply this inequality, that this should be greater than or equal to 0, for every pair of connected nodes, not disconnected nodes, for every pair of nodes that are connected by an edge with some delay or W, every pair of nodes that are connected by an edge with a delay W, you have to ensure this. Then you get a series of inequalities. The inequalities, you can give it to a computer, it will give if the inequalities have a common solution, then it will give a solution space. You can pick up any choice of R U, R V and like that for all the nodes, and thus change the value from W to WR for every edge, and you get a retimed circuit. If it is retimed, it will be equivalent, but remember, node V will produce an output here now, that will be not same as the original node V output, in the sense this one will be delayed by, this will be nothing but delayed version of the original one that comes out of V here. It will be delayed by how much time? R of V, that is the retiming value chosen here. Similarly, here, if it is node is generating some output, here also it will generate same output, but it will be delayed version of this, delay by R of U. So, every node output will be delayed by its retiming value, but since retiming values are chosen by you, you know them. Since retiming values are chosen by you, you know them, and therefore, I mean they will be equivalent, because from one delayed one you can get back the original one. All right. Now, how it comes up? First, let me give it. That is a bit lengthy, with involved proof. This is called retiming theorem. So, I am going to give you retiming theorem proof, and it is not given in books. I worked out a proof. So, be with me, because I still feel that, I mean, I should give a proof so that you really understand where from it comes. You are convinced that this works. Then we will start trying to understand the implication of this result, its I mean various possibilities, pros and cons, other things, and then how to do a particular kind of retiming, where we will follow this kind of this retiming theorem, but choose these retiming values in a particular way, leading to what is called cut set retiming, and use it to retime certain circuits, and I will take up some examples of retiming also. Okay. So, that will be the proof. Suppose you are given a DFG, n nodes, node 1, node 2, node 3 up to node capital N. Ith node produces a output sequence VIN. So, node 1 produces V1n, node 2 produces V2n, dot dot dot, node I produces VIN, and they are all connected. This is DFG of total n nodes. So, if you focus on a particular node, say ith node, it will be like this. I take the ith node as my center of focus. It produces an output VIN. Okay. Other nodes are here. I write separately, node 1 dot 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 node j dot 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 node n, all right. There may be or may not be a connection from node 1 to node I. To be general, I make provision for a connection edge. Again, if there is an edge, there may be 0 delay or some delay. So, I keep a provision of some delay A. Since it is going from node 1 and going to I want to bring subscript where it should be both I and 1 should be present, and I write this way AI1 number of delay. So, AI1 is an integer either 0 or positive, that many number of delay AI1 which goes from node 1 which is present in the edge that goes from node 1 to node I. If there is a 0 delay, you just happily take this to be 0. So, 0 into D 0. So, this is the delay free edge. Otherwise, if it is 1 delay, this will be 1, 1D, 2D, 3D. If there is no connection from node 1 output to ith input, in that case, you let this AI1 go to infinity. Infinite delay means signal from this side can never reach this side. So, if you want to make it, I mean you want to make sure that there is no connection, in all the maths we do, we will let this A fellow AI1 go to infinity. Okay. All right. And similarly, from everyone I am taking a possibility, this will be A I j d. Again, this can be 0, 1, 2, 3 or infinity. Infinity means no connection. Okay. This will be A I n. So, I is the first index in all of them, that many delay, all right. So, this fellow is node 1. So, it is also generating V 1 n, because if node I generates V I n, node 1 generates V 1 n, this generates V j n, this generates V capital N small n. Okay. This itself can depend on, there can be feedback from its output to itself, because it not only may depend on other node output, it may depend on its own output, and in this case the delay will be A I, the destination node, again I, this is a source node, destination I here, source from here I, AIID. AIID can never be, it has to be greater than equal to, it has to be greater than 0, it cannot be 0, has to be greater than 0, it cannot be 0, simply because suppose it is 0, so there is a delay free path, and so VIN, I want to find out VIN, that will depend on VIN itself, because there is no delay path. So, output, to calculate output by this node, I need the same output at the input, but that is not possible, because output has to be calculated first. That is why if it is one delay, no problem. VIN depends on VIN minus 1, which was calculated here in the previous cycle and now made to appear here. If it is VIN minus 2 here, no problem, it is 2 delay. But if it is 0 delay, it is a delay free loop. Delay free loop is absurdity, because your output goes back to the input without delay. So, output depends on output. To calculate output, we need the same output as input. So, if output is not known, I cannot calculate. So, it is a contradiction. That is why this must be greater than 0. If there is a self loop, the corresponding, delay must be greater than 0. And then there may be an external signal source, I call it S. So, there may be an edge coming from there also with some delay B I. Here I am writing only I am not putting any second index, because here the node is fixed, it is a particular node, specific node, signal source node. It does not have any index like 1, 2, 3. So, but when I look at the figure B, B means edge in the path, in the edge from source, signal source to ith node, that denoted by B, others are by A for small a coming from node to node edges, small b coming from external signal source to the node, that edge, I because it is going to ith from our external source S, Bi times D. If Bi is 0, 0 delay, if Bi is infinity, no connection, that means this particular node does not take anything from external signal source. What it does is, ith node takes all these fellows, all the information including this, and does some operation to calculate VIN. That entire operation, it can be small operation, it can be very large complicated operation, that I am not going into, that is all inside the node. That entire thing I am representing as a function, that is VIN, it evaluates a function for the ith node, some function which you know very well what it does inside, because you design the node. Function, it takes all these fellows as input. What is this fellow? If it is V1n, it will be I1 cycle delayed version of that. So, V1 n minus AI1. Dot 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 Vj n minus Aij dot 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 V capital N small n minus Ain. Okay. If you want, you can write this one also, Vi itself n minus Aii dot dot dot, and lastly, if it is generating a sequence xn, xn comes with a delay here. Okay. This is a particular node I, that is the function, but then I could be 1, so node 1 would come here, I could be 2, node 2 would come here. I am just showing at the center of focus. So, I am just considering a general case. So, these are the delayed things that are coming and delayed signal, and then this node does some operation on that, which I include in this function fi just to indicate that net operation done on that, and output comes. We will then apply retiming formula on this, change the delay values by the formula after choosing some retiming values for these nodes. We will get another structure like this, and we will show both are equivalent. Okay, that will be done in the next class. So, please come prepared with this. Thank you very much.